Hello everyone, my name is Sid Kelani and this is my video demonstration for task 8.1b. Here we start with the part A, which is basically about the counting the shortest path. In part A, the problem was to find the number of shortest path from the train station to every hotel in the graph. Since every edge has a unit weight, I used BFS instead of Check's algorithm. BFS is suitable because it explores the graph level by level, meaning the first time a node reach it gives the shortest distance to that node. In my solution, I used two arrays, one array called distance to store the shortest distance and another array ways to store the number of shortest path. Initially, all distances are infinite and always are 0. The source node get distance 0 and ways to equal 1. During BFS, if I discover a node for the first time, I set its distance and copy the number ways from previous node. If I later reach the same node again, then I add the number of ways from the current node. This allows the algorithm to count all shortest path correctly. Let's talk about the complexity. The complexity is big O bracket n plus m because each vertex and edge is processed once using adjacent list. Now we focus on the part B. In part B, it's basically about the testing connectivity. The task was to determine whether a communication network graph is connected. I again use BFS because it is efficient for graph, traversal, and connectivity checking. I start BFS from any node in the graph and mark visited nodes. If BFS can visit every vertex, then the graph is connected. If some vertices remain unvisited, then the graph is disconnected. Here, the idea is that connected graph, every computer should be reachable from every other computer. Since BFS checks all vertices and edges once, the complexity is also big O n plus m. Now let's focus on the part C, which is basically around the DFS with the adjacent matrices. In part C, the question asks for the runtime complexity of DFS when the graph is represented using an adjacent matrix instead of an adjacent list. So yeah, basically answer is O n square. The reason is very simple. That for every vertices, DFS must scan the entire row of the matrix to check possible neighbors. Even if an edge does not exist, the matrices position still need to be checked. Since there are n number of rows and each row has n number of entries, the complexity becomes big O n square. Let's focus on the part D, which is the Dijkstra algorithm. In part D, I solved the shortest path problem using the Dijkstra algorithm starting from node 1. Dijkstra is appropriate here because all edges weights in the graph are non-negative. I first converted the adjacent matrices into direct weighted edges. Then I followed the standard Dijkstra process where the algorithm repeatedly moves the unsettled node with the smallest temporary distance from the priority queue. Starting from node 1, node 2 gets distance 4 and node 6 get distance 10. Next node 2 is removed because it has the smallest current distance. From node 2, node 4 becomes 9, node 5 becomes 15 and node becomes 12 and node 8 becomes 14. The algorithm continues until all reachable nodes are processed. The priority queue removal in my solution is 1, 2, 4, 6, 3, 7, 8, 5, 10, and finally 9. Node 9 is unreachable from node 1, so its distance means like remains the infinity. The shortest path tree is formed using the parent edges discovered during relaxation. For example, 1 to 2, 1 to 6, 2 to 4, 4 to 3, and 5 to 10 shows that it works efficiently here because no negative edge weights are present. Here, let's talk about the part E, which is basically around increasing average age weight. In part E, the question asks whether a shortest path remains a shortest if average age weight increases by 1. The answer is definitely no. This is because different paths may contain different number of edges. A path with many edges receives a large increase compared to a path with fewer edges. In my example, the path from S to A to B and to T originally had cost 3, while the direct path had cost 4. After increasing average age by 1, the 3 edge path becomes 6, while the direct path becomes 5. So the shortest path changes. Now let's talk about the last part, part F, which is basically around the negative cycle problem. In part F, the graph continues exactly one negative cycle, and the goal was to determine whether a negative cost exists from the source to the distance. My idea was first to check whether the negative cycle is actually usable. I perform on BFS, one on BFS or DFS from the source node to determine which vertices are reachable from the source. Then I reverse all the graph edges and perform another BFS or DFS starting from the destination. If a cycle vertex is reachable from the source and can also reach the destination, then the negative cycle can be used in the route. In that case, the route can loop around the negative cycle many times and make the total path cost negative. If the cycle cannot be used, then I apply Bellman-Ford as a backup, like to check for other negative cost paths. Bellman-Ford is suitable because it can handle negative edge weights and the total complexity becomes the O big O and M because Bellman-Ford dominates the runtime. Overall, this task helped me understand how the graph traversal and the shortest path algorithm work in a different situation. Thank you.